Hey, welcome back to the academic powerhouse with your mathematical meathead himself, the realest guy in the room. Bada bing, bada boom. How you doing? How you doing? Let's continue on with a couple more important notes about statistics as our journey comes to an end on our unit on statistics. Okay, so let's remind ourselves of our journey thus far. Statistics is all about our ability to tell a story of truth through data, through collecting, analyzing, interpreting, and presenting data. And like any good story, it has three elements. All stories have characters, conflict, and resolution as their three elements, but our stories of statistics have the elements of center, spread, and shape. And so, what we have done along our journey thus far is we've been able to collect data through answering a series of statistical questions. Statistical questions. We recognize that statistical questions have variability in the answers that we get depending on who we ask, depending on the context. How old am I is not a statistical question, but how old are the students in the class? You can have different answers, and therefore that variation makes it a statistical question. We survey people, we poll people, we get data, we've collected the data. We've also analyzed data when we talked about calculating, or when we talked about in depth center, spread, and shape, we talked about how we can calculate these two, center and spread, right? We have our mean, our median, our, our mode, we have range, interquartile range, and we have mean absolute deviation, right? Remember all those? We spent some time calculating that. When we calculated it, we ended up getting a shape, and therefore we had our three elements. Right? We were able to analyze things by taking those numbers and performing calculations. Now we're at a point where we can interpret data, and we can interpret data by looking at the relationship between spread, shape, and center. They all related. When you see it all laid out, you can see the relationship. You can begin to interpret what's happening with your data, and we can then therefore check off interpreting the data. Right? So let's think about something a little bit more thoroughly, okay? Now, this relates to what we're going to talk about a little bit more, but I have taken the liberty of baking us some delicious and yummy cakes. Yummy cakes. Now, there's all sorts of cakes out there in the world. They're all beautiful, just like many things in math are beautiful, right? But both of these cakes have a slightly different story to tell. Have a slightly different story to tell, which brings us to statistics, right? Well, actually, before even bringing us to statistics, the story of these cakes might be one of this one here looks a little crazy, looks a little fun, looks a little wonky maybe, but still delicious and beautiful. This one here looks very royal and regal and definitely high class and elegant. So you got some story going on there. And just like our statistics, there are different stories to tell based on what our center, our spread, and our shape are to be. But let's review a little bit here. Our fundamental distributions, our fundamental shapes that we've come to understand at this point in time. We've got up here, we've got some dot plots, and we recognize those dot plots come in all different sorts of shapes. We have our stem and leaf plots, and we also recognize that they come in many shapes, along with our histograms over here and our box and whisker plots over here. Each each representation has a different story to tell. We can make different interpretations based on what we see and what we have calculated. So, does anything stand out to you as when you look at let's look at these histograms real quick. As far as the shape is concerned, does anything maybe stand out to you as to how they differ? You could even with these dot plots here, and I'll even draw the shapes a little bit here so it's clearer to tell. Right? Does anything perhaps maybe stand out about the shapes? Think about that for a second. Pause the video if you must, so we can think here. All right, let's talk about things. Well, what I see right off the bat, and this I'm just talking shape here. I'm not even talking about the calculation, but the shape itself indicates some degree of symmetry. Yes, yes, symmetry, symmetry. Let me even write that word. It is a key word for us to understand. If you're not familiar with what the word symmetry means, it means the evenness of a shape's appearance. Uh, for example, here. Now, I'm not saying this is perfectly symmetrical, but it is relatively symmetrical. Look at this. You have a very clear middle. You have what appears to be a fairly even amount of data points off to the left of it, fairly even amount off to the right of it. Again, not perfect, but fairly symmetrical. The difference being, of course, if you compare it to this one, for example, this one you can clearly see there is a, a center that is really off toward one side. You can see that there's a bunch of different data points off on the right side and only a few on the left. And similarly here as well, center is off on to the right, lots of data points here on the left. So these appear not to be symmetrical, these two here. In fact, those would be considered asymmetrical. And you can see, even with these dot plots here, there's one here that appears a little bit more symmetrical than the rest. If a fairly clear idea of the center, fairly even, perhaps, well, not perfectly even, but fairly even amount of data points or dots off to the sides here. You can tell that, these ones are fairly symmetric or asymmetric, going off to one side. Same with this one, and so forth and so forth. And these box and whisker plots translate into something that looks like this. These ones sort of look like this. This one here looks something like that, right? There's some symmetry, there's some asymmetry, and because of that asymmetry and symmetry, there's a different story to tell. There's a different story to tell, and it can be the same sort of question, the the questions that we've become familiar with, heights and shoe sizes and ages and test scores and all these different things, but because of the differences, we can have a different story to tell. So let's look a little bit further into what it means when something is symmetrical. Symmetrical. Well, what it means is that when you do remember your calculations of center and spread, when you have a very perfectly symmetrical distribution, we'll call these distributions or visualizations if you want to stick with that. When it is perfectly symmetrical, what you are saying is there's an even amount of data points off on the side of what we've determined to be our middle. Perfectly. So let's say we have 90 students in the class and we're talking about their test scores. Well, what we're saying is Um, whoops. What we're saying is exactly half were less than the middle, exactly half were above the middle. And most significantly about symmetrical shapes is that when you do your calculations of center, you'll see that the mean, the median, and the mode are all exactly equal to each other. That makes sense. It should maybe make some intuitive sense, right? Because if you have everybody, or let's see, or most people scoring one way or the other, and a few low or a few high, well, then that could maybe throw things off a bit. But here it makes a lot of sense, right? The most common value would, so in other words, the most common value would be directly in the middle being the median, and the average being that 50%, the halfway mark, right? Things make sense. So I guess the big takeaway here is that besides knowing that these are all equal to each other, I'm not sure why this says zero. No, they're all equal to each other. They're all equal to each other. So the big takeaway is that this is normally normal distribution. You could even say it's in balance. You could say it's symmetrical. You could say there's no skew. You can, again, the takeaway is to know that this is a perfect model, perfect representation, and that all of our measures of center are equal. And there you go. That is symmetrical. Now, here's where things get a little interesting, right? When it isn't symmetrical, when it is in fact skewed or asymmetrical. So here's an example of, for example, a right skew or a positive skew. So how do we interpret this? How do we interpret this? Well, let's think about test scores, for example. So we've got a lot of students in our class. We've got a lot of students who do their best, do as good as they possibly can. But some, as we know, some quizzes and tests are much more difficult than others. But there's always a couple of students who just seem to do well all the time, to, even though everyone else maybe not as well, right? So for example, when you have those students who do so phenomenally well, ace the test where everybody else is getting maybe a C on the test, they can throw off our whole data set. They can because they are way out here, it's skewed when you calculate the average, right? It just gets skewed, right? You know, you got 75 plus 75 plus 75 and then plus 100. Yeah, it's not a true representation of what most people got because this one number throws it off, right? When you're doing mean, right, divided by, let's say 30, right? This number, because this uh, unrealistically inflates the numerator, right? When you have a bigger numerator than a denominator, your mean or your uh, quotient becomes larger. So this makes sense. Your mean is much larger. It's thrown off because of a couple high achievers. And you can even think beyond simply just test scores, right? Think about the bosses at the companies. The bosses make so much money. The CEOs, they make so much money compared to the average worker, right? It's not fair to include them in the calculation of what the average person gets because, right, the CEO is making millions of dollars and everyone else is making 50,000, 60,000, somewhere in there. So to include them, if you could include them, you'll then calculate an average to say that everyone's making around 120,000 a year. No, no, not at all, in fact. So again, I guess the point there is to say that, listen, when you have some extreme values, when you have some extreme outliers way out here, just a few of them, could really, You could really bump up your mean, but that's why we have multiple measures of center, because the median is the exact halfway mark, right? No, remember when we were calculating them, it always was the the halfway mark. We the number of data points. Let's see, we have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. We have 11 total. This was our Q2 or median. Remember that? Exactly the halfway mark. That is it. That is it. That's why we have multiple measures of center, and that's why it's useful to say what the median is at times, right? Because if we lined up all those test scores, we would see, okay, the median is 75, 78-ish. Or we lined up all those salary values, and we'll see, oh yeah, the median isn't $2 million a year, or 30,000 a year. It's more around 45,000 a year. So median is important to get a very accurate representation of where the true middle is, as opposed to the average. And then the mode, it would make sense. It would make sense that the mode is over here. Over here, mode being the number of occurrences, um, uh, the occurrences most often. So the test scores that have most often occurred. It would make sense that it's lower than the median because you have to have it balancing out against the really high extreme mean. Or you have to have some stuff back here to kind of counterbalance what's all happening here. Some of these outliers here counterbalancing here. And so there you go. So this general idea of the mean being really large in comparison to the median and the mode, it makes a lot of sense. When you have, so the shape overall results in a skew, an asymmetrical sort of appearance. An asymmetrical sort of appearance. It's skewed. It's skewed in the positive direction, right? That really high test score skews it more positively than the lower test scores would otherwise indicate, or that really high CEO salary skews it in a way that is much more higher than it otherwise is in reality. So those are some of the interpretations you can make from asymmetrical right skews, but there is an asymmetrical left skew, or a negative skew if you want to call it, and it's the exact opposite of what we did up here. It's the exact opposite. Whereas, let's say we had a test or a quiz, and most everybody did wonderfully. They did, amazing, got amazing high scores. But we had a few people who just, for whatever reason, they were having, um, a bad day, or whatever the case may be, and they didn't score as well as most, right? They scored super low in comparison, right? A couple zeros on a quiz, a couple zeros on a quiz hurt a lot, the average. They hurt when let's say your average is 88 plus 88 plus 88 plus 88, right? That has a huge impact because even with that zero, you're still dividing by the same amount of test scores, but now you've given up 88 points in the numerator to balance it out. So I guess what I'm saying there is you have a lot, or even some really, not even a lot, but just even a couple really, really low ones is going to push the average downward, right? I say push it downward because remember, symmetrical, it's the same, mean equals median, right? But a couple of those zeros, a couple of those outliers on the lower end will push it downward, that mean. So that's the idea there, guys, is with these left skews, a couple of really low or more negative, more negative values, relatively negative. So Now your median, again, that's why median is more of an accurate representation, is because, yeah, you may have a bad one or two here, right? But most people got, let's say that 88. So it's important to be able to say multiple measures of center because because then you have a much more full picture. You have a greater story to tell. The story I can tell with just this one is exactly kind of what I've been saying. Yeah, we had a couple bad scores, but most people scored really high. That's the story to tell if this were a distribution of test scores. Similarly, like I said above here, the story to tell is, listen, we had most people were we had some really high ones, but most people sort of fell into um, sort of an average range, or like a 75 range, for example. I think I had up here 75. So yeah, some people did really high, and they kind of skewed the numbers a bit, but most people were right on target where they should be, 75. See, so there it is. That's the importance. That's the importance of understanding, or that is the importance, but it's also just a better sense of the relationships of these different measures and the spread, the shape, I should say. And now let's talk about real quickly the relationship of shape to spread. I think I may have touched on this a little bit in a prior video, but here's the idea. Uh, let's say I have a perfectly symmetrical. I'm just going to work with symmetrical distributions at this point. And then I'm gonna have three different ones here, and I'll explain. That's kind of, sorry for my artistry once again, not the best artist in the world. There we go. All right, that looks to be about correct. So actually, no, I'm gonna do these in different colors so it's more easy to see. So let's do, there we go. All right, so you can see different shapes and different spreads, right? So right here in the middle of this green one, this is the middle of the green one. Spread, once again, refers to the distance of the data points from the center. So I'll do this and this. Once again, uh, so for this red one, the center here, right, the center, these are all the center. These centers overlap. So for this red one here, this pink one, right, you can see the spread looks visually more. Now let's look at this black one here real quick. So again, the centers all overlap on top of one another. You can see this black one here. There you go. So what is the relationship between shape and spread? Well, the relationship between shape and spread is you can kind of see as I was drawing it out, right? The the more spread, the more spread there is, the shorter the center is, the shorter the middle is. So I'll even write that down. More spread equals shorter uh, center bump, we'll call it. And then less spread as with the green one, equals tall and skinny. Tall and skinny. So you can call this, I guess, if you want, I guess you can call this short and fat if that makes a little bit more sense to you, I guess. Let's do that. That makes more spread equals shorter and wider and fatter. Less spread, as with these green ones, and you can see, right? Red was a little bit shorter than black, and therefore it was a little taller. Green was even shorter than that as far as spread goes, and it was even taller. The reason is because the reason why it gets taller is because all of your data points are now at that center. More data points, right? Remember dot plots? Remember dot plots, right? If, you know, with each data point, you get more and more and more and more taller. And there's less out here, right? So that makes sense, right, guys? Right? So you're taking all your data points from here and you're moving them in here. Well, then you have, right? So it would make sense that it's getting taller and therefore skinnier, right? Makes sense. Anyway, so remember this rule of thumb. The relationship between shape and spread is more spread, shorter and wider. Less spread, you get a taller and skinnier. The relationship between shape and center, I'll even write these out. Shape and center results in skewness. Oh, that's horrible handwriting. Skewness. Shape and center results in skewness. Skewness. So there you go, guys. That is the relationship. That is how we interpret data. In fact, I'm going to check it off. We have successfully interpreted the data. We have interpreted the story of the test scores. We have interpreted the story of the pay disparity between bosses and regular workers. Now, the last bit of our statistical story is all about presenting the data, presenting it via charts, via pictures, to whoever, right? And that's far beyond the scope of our particular class. Our scope is mostly on collecting, analyzing, and interpreting data, and we have done so. We have done so. Our journey has come full circle, guys. Now, with that said, I may go into a little bit more topics that you may learn in the next grade level. Just a few. We'll see. But either way, I hope this does in fact bring things full circle to you. This does sort of give you a nice broad overview of statistics and the fact that you can tell a story from it and the fact that there is meaning behind these three different elements in the stories that we tell. And I hope throughout this whole journey that you've built up your mental muscles towards statistics, that you felt the burn day in and day out, video in and video out. The practice problems made you sweat. The length of the videos made you cringe. No, I'm kidding. But seriously, in all seriousness here, I do find statistics to be the most enjoyable aspect of math because it is storytelling at its core. And so I hope you've gained that appreciation for statistics over our time together. With that said, that's all I got for you guys. I hope to see you in the next video and take care. Bye.